Okay, very good. First, I want to give an attribution to Mr. Ron Bernstein Consulting Group for assembling these initial slides and doing the bulk of the work for us here on this presentation. Ron is not only head of his own consulting group, but Ron used to be the executive director of Landmark International for probably 5 or 6 years. And now he has a role with Landmark as the chief ambassador. The ambassador program is a relatively new program that we have going on now, and we're pretty excited about it because it allows folks to really get out there around the world and help us drive some of the message of Landmark and what it's all about and what we can do for folks. And they do this on a volunteer basis. Both in terms of geographies, we have folks all around the world, in Spain and in Japan and Denmark and South America. So we have folks everywhere, and we're constantly increasing the geographies they cover. The other aspect is by industry. So some of them might focus on systems integration. Some of them might focus on the utility side of things, generation, that sort of thing, and demand response. And others might focus on specifications. So we have a great number of wonderful people who are working in that program. So just that attribution to Ron and his group of folks. And without further ado, we'll get this ball rolling. So thank you all for attending today. It's wonderful to have you here and have you interested in this. We're going to talk today about the power of profiles, and we're going to do it in what's known as the black box concept that Ron has put together for us. This is a nice way of looking at profiles and what they can do on a micro scale as well as a macro scale. So in doing so, we need to begin to think inside and outside the box. Basically, what we're looking at is a way of modeling devices in a way that talks about the inputs and the outputs and what it means to define the functional aspects of something like a thermostat or an air handling unit or something of this nature, or even a lamp. But we want to take that a little bit further and talk to you not only about devices and profiling what they do, but profiling subsystems and even systems. And we're going to look at this in a way that shows you the modularity of how these things are modeled. And we're going to talk about how that can improve integration and interoperability by having that common representation. And then we're going to look at how this really affects the specifications that come out of this kind of a process. And the reason this is so important is because the specifications are what drive the industry. And if things aren't being specified, it's pretty rare that things will be pushed from the other side. They need that pull, specifications, and the pull of an end user to want to have this modularity and to have this interoperability. And so we'll talk about this in context with that, jumping back into how that relates to specifications and specifying these types of things. So let's get started. We want to look at things in terms of 3 different levels, or 3 different tiers, if you will. And we'll take energy and control in this aspect. When you look at building systems, they're comprised of quite a few different pieces and parts, subsystems, if you will, or at least sub-functionality, things you want to accomplish. So when we look at this, we look at things such as demand response, heating, ventilation, air conditioning, lights, parking, watering of plants and grass. We look at metering. We look at a lot of different pieces and parts to it. But there's another aspect to that, and that's dealing with what all those things relate to. So, for example, when we look at HVAC and lights, we understand that they relate to an indoor facility. We understand that these are the kinds of things you're going to find inside a facility. And so you start to think about things in terms of modularity of not only the subsystems and the devices within those subsystems, but moving up the food chain, if you will, up to the site level, and then looking at ways of trying to get that information up even further so that it can be analyzed and recorded and looked and addressed for trends and other types of things. So basically we're trying to get the information all the way from the subsystems of heating, for example, all the way up where we can begin to look at these things in a more holistic approach, where we can look at the alarms and look at the performance and what this really means to the bottom line. So take a look at these three different aspects, if you will. When we're looking at building data abstraction, we want to look at it in three basic tiers. And now you can look at it in a number of different models and divide this up as much as you want. But basically there are three levels here. And I'll start at the bottom at tier 3. We look at a device level. When we're talking about sensors, we're talking about actuators, we're talking about controllers, we're talking about the things that we need to interconnect. And those need to be profiled. When we look at the second level, the tier 2, we're talking about building infrastructure. This is the connectivity side of things, where you're trying to tie in these various things over perhaps Ethernet and over Wi-Fi and maybe native protocol types of communication. The next level is a tier 1. You look at the enterprise or site level connectivity. And that gets into an even more broader WAN type of concept, a wide area network concept, and how you deal with inter-building connectivity. So those are all very important unto themselves, but we need to look at them in how they interconnect, and that information that's shared between them is critical. And the people putting in the tier 1 systems are not necessarily the people putting in the tier 3 systems. And so that ease of communication between the different systems, the different tiers, are extremely important. Now, when you look at the, jump ahead here, when you look at just the tier 3, for example, you see that there are a number of different pieces and parts to this. There are different players involved in this. Those who put in the direct digital control devices, those who put in the mechanical and electrical pieces. And if you just look at the devices, there's a myriad of subsystems within here, as well as devices that comprise the heating systems and the lighting systems and meters and so forth. And so there's a lot that needs to be relegated to just that tier 3 end and not pushed up into a tier 2 or tier 1 model. Those need to be separate. Keeping in mind, of course, that you need to share that information. So we need to look at the elements that are common across these different things. We need to look from two different aspects primarily: a logical interface and a physical interface. In terms of the logical interface, we really need to look at what are the data coming in, what are the data going out, how do you configure a system so that you can minimize bandwidth or prevent too much data from being shared across the network or just an overload of data. And then you want to look at how you manage what you've collected. What do you want to do with it, trending, logging, and so forth. Then from the physical aspect, you need to understand the low-level portions communicating directly with the sensors and actuators. What are you sensing? What are you driving? How do you know one device from another device? Are there any types of feedback locally on a user interface display that gives you any idea of the status of the device or the status of what it's reading? How does it interface with the network physically? And where's it going to get powered? So you need to address all those different things. But when we talk about profiles, we're really talking about what's in the box. And the box we represent here in this black box concept for a reason. It's because on the outside, you shouldn't have any idea what's going on the inside of that box. Aside from configuring the box, providing it some inputs, reading some outputs, it's really a black box. It's up to the vendor to determine what's in that box and how it performs, and up to the end users and specifiers to be able to pick the best of breed from these different systems. So we represent here a couple different things. We represent the device, the subsystem, and the system. All three of these different things can be represented in the same exact black box profiling concept. So we need to look at the logical interface when we talk about what's in the box. This is, of course, the data that are shared in and out of the device from a network standpoint. We also need to look at it from a very physical standpoint. The physical interface is important. What are these 1 to 10 volt inputs? What are these 4 to 20 milliamp inputs? What are these on-off types of inputs we're getting, binary inputs, as well as what's going to interface to the top. Is there an LCD? Is there a blinking LED? We need to know these things. And then, of course, you have to have control algorithms inside that deal with it all, and a way to configure those control algorithms. So moving one step further, when we look at this black box concept, all of these are true for a device, but they're also true for the subsystem at large, and the system even larger. So if we take the logical interface and we combine it with the physical interface and we throw in some control algorithms, we get a complex box. We need to look at it in pieces and understand how that can grow in a much bigger picture. Do I care what's in the box? Not really. From a systems standpoint, I don't really care what's in the box. I do need to know that it performs the required functionality. I would rather it not be proprietary, though the algorithm certainly can be. Can it be replaced with another device? Is there an interchangeability as well as interoperability? And that's important because the two are often intermixed and confused, but they're rather different items, where interoperability is really all about being able to coexist and share information. But interchangeability is it's the principle of being able to swap one device for another. So we need to look at what the goes intos and goes outos, as you see on the right-hand side. What goes into the device and what comes out of the device. And how do I interact with those? And then what logical options do I have to work with here? What can I do to throttle the information or speed up the information? Or get a heartbeat so I know that the device is still sensing information at a rate that's acceptable to me. And then I need to look at, of course, physical requirements of the device. So there are a lot of aspects here when I talk about the black box in general. But I don't need to know so much about what's in the box as an end user, as a specifier. But as a developer, of course, you do. So let's look at profile and modeling for just a moment. Let's take the logical interface at first here. Let's look at the data that go in. Typically something like commands to do something. Or it could be a subscription to some sort of change in value of data. That's important. Then we look at the data that come out of this. It could also be a state change. It could be here's my broadcasting or my subscription output of what's going on inside. And that's usually a lot better model than a command coming out of the device. It's certainly better to have your device state its temperature than it is to say it's too hot. It's also better to have it state its temperature than to say turn on the air conditioning system. Because you don't know necessarily how many devices might be connected to this and how they're going to use that temperature information. It might be absolutely perfect for a greenhouse application for that temperature to rise beyond what would be acceptable for a wine cellar. So it's important to not assume when you're creating a device that this device is going to be used in any given application that you can imagine. It may be used in a breezeway as a temperature sensing device. It may be used in a wine cellar as a temperature sensing device. It could be used in a smelting facility. You just don't know what its purpose is when it's finally installed, and so you need to make it flexible enough that it delivers information about status and its state as opposed to sending out commands. And this is all done through configuration. Being able to set these different set points, alarm points, being able to determine who gets to access this information and what kind of security is around this information. If it's something that needs to be authenticated or something that needs to be encrypted, for example. All of that information should be field adjustable, not necessarily put out or put into the device at the time of manufacture. And then the other thing you need with a logical interface is to understand the management, identification, the who, what, wheres of the device. You need to know the health of the device, and you need to know, of course, is it doing its job. Now let's look at the physical interface. Physical interface is fairly simplistic in terms of how you deal with it. It is the core of how this interacts with its immediate environment. Not necessarily its greater environment, which you'll find in the logical interface, the network environment. But from the physical environment aspect, you need to look at the sensor inputs. Digital inputs, I/O, analog inputs, what type, and then you need to look at the outputs. What are you trying to drive, and how are you going to drive it on a physical level? And then you need to figure out what it is this is actually trying to control. I can run an algorithm internally and report or do something. Schedule, PID. This is the type of things that make the black box do what it's supposed to do internally. And of course, there may be physical identification as well. Where is it physically located? How is it defined where it's physically located? This could be done by interfacing, dip switches, any number of different things. And as you get more into the logical interface of identification, the less you need to deal with the physical interface of identification. So let's look at this black box again with the devices in the subsystem and the system. Let's take a look at some more detail. Naturally, we have to have the control algorithms, and those are going to be what they are, for logging, alarms, and other types of actions. We also have, of course, the physical interface, as we just talked about, sensors in, actuators out, power in, network in and out, and then, of course, the logical interface. And it's the logical interface I want to go into at this moment. If we were all in the room together, which would be great, would be looking at the list of attendees here today. I know quite a number of you, and I think it would be a great time for us all to get together and just hang out in the room together. But if one of us were to come into that room carrying this particular object, I think the majority of us could probably look at this and we would know what it is, we would know what it's for, and we'd have a pretty fair guess if we heard it sloshing about what was in it. And many of us might be inclined to leave the room, especially if anyone were smoking in the room. Because most of us know this as a gasoline or petrol can. And we know this because of its size and shape, its color. There's a lot to this can that immediately brings to mind exactly what's in it and exactly what it's for. It is a container, and it is the type that is designed for carrying petrol or gasoline, and it is most likely carrying some type of gasoline, kerosene, or petrol. And we know that because of the container shape, what the content of the container would be. If I were to tip this and orange juice would pour out, that would not be expected. So we need to understand that this is really all about what you expect the container to carry. And this is how a profile gets its information from one point to another. So let's look at the word bonnet for just a moment. The word bonnet in English has a whole lot of different meanings. And in order to understand all those meanings, you have to understand the dictionary definitions of those meanings. You also have to understand the context in which bonnet is being used. Because as you can see, there's so many different terms that have a lot of different meanings. And this is just one term, bonnet, that has such a meaning. So So what we need to do is define which bonnet we're talking about if we're going to be talking about a bonnet. It's not enough to have all the different dictionary definitions, but we need to understand how they're used. Let me explain what I mean by this. In the LawnWorks world, and it's different in different technologies, but in the LawnWorks world, we deal with things called snivets and skivets, standard network variable types, and standard configuration property types. These are basically words in a dictionary, where we have snivet temp P, and a dictionary might have the word bonnet. Snivet temp P represents a precise HVAC temperature and a defined range and resolution. Bonnet, in the dictionary, has a lot of different meanings, but we're going to pick one, and the one that we're going to pick is a metal cover for a vent, fireplace, or car engine. Another example would be snivet angle. It's in rotation, or phase, in radians. Could we have used degrees? Sure, we could have, but we use radians as an SI unit. And that's what we use as our definition for a snivet angle. For those of you from the Midwest of the United States, you'll recognize the term pop as a soda, a soft drink, Coca-Cola, for example. But from other places in the world, a pop might be somebody's father. So once we have our dictionary, and our words in our dictionary, and our particular definitions in our dictionary, then we need to be able to put these into sentences. And sentences are what we would consider to be network variables or configuration properties. These are basically the content of what you would find in that gasoline can, that petrol can. The petrol can is your snivet. The content of that is your network variable. What's delivered from the spout, if you will, is the network variable. And this is an NDO temp, as this example. It's an output data point, a temperature value. And our sentence on the right-hand side is lift the bonnet, or raise the hood. Okay? Or NCI default, which is the network configuration input of a default value, and it'll be a default angle value, and it's to be stored. On the right side, I want some pop. My carbonated beverage is desired. It doesn't mean I want somebody to punch me. It doesn't mean that I would like a new father. It just means that I want something to drink. So there's a lot involved in the sentence and how this is represented. It's not enough to know a temperature, but you need to know that it's an output temperature, and you need to know that it has some context related to the carrier in which it came. But that context goes a bit further. It's not enough to lift the bonnet, you need to know why. Lift the bonnet for repairs. It's not enough to have an NVO temp. You need to know what it's for. NVO room temp. It happens to be the desired room temperature, throttled by a minimum set time with a restricted range. And that room temperature is what we're reading. So our profiles create the context for these sentences and these words with particular definitions. So let's look at it here for just a moment in our black box concept again. We have our control algorithms. We have our physical interface, where our sensors, user interface, power network communications, etc., are involved in inputs, and we'll represent them coming in from the bottom, and our actuating outputs. These are our 4 to 20 milliamp or 1 to 10 volt. And then we have our logical interface, where we have inputs and outputs that are mandatory data values. And then we also might have a kind of a value add, if you will, of optional things that a vendor could include, but fully defined so that it could be used in a network. So if we take these concepts and we put it all together, we've got our inputs and our outputs for our logical interface, we have our physical outputs and inputs, and we have our control algorithms. And this kind of represents what the black box model would be for a device. This allows us to take what it is we're trying what's controlling this device on the left-hand side, and push that to how you would monitor this type of information on the right-hand side. This is including, through the algorithms, all of the different things that we're trying to sense and all of the things that we're trying to drive locally. And this model can be expanded not only at the device level, but we can expand this at a number of other levels, so long as we keep in mind these best practices, where we want to try to make sure that we have the functionality and performance necessary to do what we need to do at the very base level, and we make those mandatory as we build these profiles. We also want to look at whether there's interchangeability or interoperability at need, and address those different types of configuration related to that. We want to make sure that we have short and long-term competitive sourcing. We want to avoid vendor lock-in, which is very important if you want to attempt an open system approach. And you want to make sure that there is some robust intercommunications and understand the needs at the different tiers we talked about for security and levels of access. Let's take a thermostat for just an example. The thermostat's got a number of different set points and the number of different schedules it might be in, with some outputs for zone temperature and set points. It might be driving a display. It might be driving an LED to blink, or other communications outward. And it might be sensing something locally, and you may have to deal with the different power inputs and other things that it's driving or being driven by locally. And the control algorithm might deal with a call for heating or cooling. You might also deal with setting things by configuration of how it's going to respond to certain things. Again, with the control and the monitoring, what it's sensing, and what it's driving locally. This could be applied to an entire heating and ventilation air conditioning subsystem as well. Looking at demand response, cooling and heating, scheduling, and looking at alarms and temperatures and status going out. Looking at basic inputs and outputs of driving a cooling and heating system, airflow, what types of inputs you're getting, and the control for those indoor air quality and comfort and conservation. Further than the HVAC subsystem, however, you can drive this even further up the chain so long as you keep to the best practices when you're designing the subsystem. Addressing how these different things are going to be managed, scheduling, alarm, the types of communication. Looking at things from a top-down look, how will you interface with the enterprise? And then developing the standards for the various pieces, visualization of the information, user interface, how it's going to integrate with an energy management plan. All of this can be applied even at the buildings level. So you can look at all of these, such as demand response and scheduling, as pieces and parts at a much higher level, looking at overrides and how the status comes out from the HVAC system and lighting system and energy systems. You can also begin to look at some of the things that you're going to control, such as process, productivity, and comfort levels, perhaps even air quality. And again, more inputs about the cost of things, how things are, the availability of things that are your resources. And your resources have a great impact on your operation. This can be expanded even. When you look at the concept of the building can have each one of these little modules within it to deal with HVAC, to deal with lighting, utilities, and fire systems, network communications. All of these things are the same model, miniaturized, if you will, at the subsystem level, where each one of these subsystems within this building box can be broken down into the various devices that comprise it, still with the same profile and model. So this looks like it's about as far as we could go. Well, not the case. Because, of course, you can bring this up to an even grander scale by looking at this from a campus of facilities. And you can begin to look at the enterprise model, where it's looking at each individual building and the subsystems within those buildings and the devices within those buildings. And each one is represented with the same model. So in order to design in this respect, we have to look at things from that top-down approach. What is it that you want to do from the enterprise level? What type of data are you interested in collecting, and why? You don't just simply want to collect all the information you can without a reason for doing so. You want to resort to such things as peer-to-peer communications where necessary, and keep some communications within a subsystem or within a building, rather than bringing all the information up to the head end where the head end needs to make decisions. So the first approach to doing this is to look at the points list. Obviously, you can't see this points list very well. It's an eye chart. But nonetheless, you'll need to create a point list or have a points list created so you know just exactly what you need to model from the top down, from the enterprise down, from the buildings themselves downward to the various different systems, and even across systems. So when you take a look at something like the building monitoring points and energy and the EMS points, the dashboard system, all of these different points need to be considered when you're assembling things from the enterprise level or profiling things at that level. So when you look at a profile of a device, it's really comprised of both the paper that it's written on, if you think of it that way, the actual definitions of what it is that we have, as well as the implementation itself. So taking a temperature sensor, for example, we're not just talking about the tiny physical hardware of a sensor that senses temperature. We're talking about how that relates in that whole context that we looked at, that larger range. And we need to keep in mind that that particular temperature is going to have some restrictions to it. It's going to be temperatures within an HVAC range. It's going to have a particular size and shape. It's going to be in Celsius, perhaps. And this is a good time to point out that if your definition is consistent across all geographies, like using the Celsius system, then when you show it on a user interface or you enter it on a user interface in Fahrenheit, and it can still travel the network in Celsius, then you don't have a difficulty between a product made in Germany and a product made in the United States, for example, trying to communicate. They'll all communicate just fine. And the user then decides the different types of units they want to use locally. But all of this needs to be defined, and it needs to be defined within the definitions. Going to the block concept again, the functional block, if you will, is just exactly what is implemented from those different rules. So the temperature sensor profile may have a number of mandatory items, and it may have some optional items. It may have some other descriptive items on how you might want to handle the algorithm. But the functional block is what did you actually implement in your device? Likewise, the data point is the implementation of that carrier description, that description of the petrol container, gasoline can. And then, of course, the data are what ride inside that data point, that actual carrier of information. What's left, however, is just that model, just what you're going to try to accomplish. What is it that you're trying to spill from that container? All of that then comes into the committees that design this and form some type of profile device, such as the sunblind controller you see here. It must provide a particular setting output. It can provide a state. It can allow for a setting to be daisy chained into it. You can group control it. And there's a number of different algorithmic configurations, such as receive heartbeat and send heartbeat, and is there a window open, and other types of input. And all of that, of course, then is defined within a profile documentation. So how do we do this? How does it get done? Well, it primarily gets done by subject matter experts. And then from there, once they've created their desires for profiling a particular function, that gets delivered to some type of a task group or committee that's going to work on this. That committee begins to work on it, changing a few things, modifying a few things, adding, subtracting, to come up with some type of industry consensus for this profile. And then there needs to be a commitment by some of those players to actually implement this, so that there is something out there that is commonized. We've done this within Longmont. We've created what we call our task groups, and our task groups have created close to about 100 profiles at this point in time from all of these different groups. These are a listing of our task groups, from automated food service equipment down to utilities, and wind generation, solar cells, including security and refrigeration systems, washers and dryers, elevators, lighting, and other types of things. So these profiles then are done by the industry experts within these different task groups. Then we verify things through a certification program. All products must comply to the profile standard. A certification program testing is required in order to guarantee that interoperability compliance. When doing this in specifications, the specifications should require particular profiles. So if there's an air handling unit, or if there is some type of lighting controller, the specifications should call out the profile. And then the specifier and the end user should validate this and enforce that they are actually using the proper profiles, and that they have a good integrator who's been trained to do these sorts of things. And then, of course, that entire set will simplify integration costs. And basically, that's how the profile concept runs its course. That's how it gets its power. I want to take some questions now. I know this is a 45-minute presentation, so we do have a little bit of time for questions. And feel free to punch those right into your questions box in the lower right corner of your screen, and I'll be happy to answer.
As Jeremy mentioned, right now, if you have any questions, please feel free to submit.
And while folks are typing, I just want to thank everyone for taking the time out of their busy days. For those of you on the west coast of the U.S. and Canada, thank you for joining. I know it's early. And for those of you in Europe and Asia, I know your days are just ending or have long ended, and I thank you also for joining today. The presentation has been recorded. It will be available online. Hopefully we'll have it up by next week, and we'll be able to download it in the webinar area. You can find that at www.lonmark.org/webinar. Either you're all writing frantically or I've answered all your questions.
Also, feel free to send an email. I believe GoToWebinar will also send out a questionnaire. We would love to hear your feedback on the content of this particular webinar and possibly any other topics you would like to hear in the future.
Thank you, Janet. And I just received a question that came in. Where can you find the profiles that are already done? That's a great question. You can go to the website at, again, www.lonmark.org/profiles. You can also find it quickly in the Jump To field, which you'll find in the upper right corner of the website pages. And you can put in profiles there, and it'll take you right to it. It'll take you to what's known as the SPID master list, the Standard Program Identifier master list. And from there, in the different categories of heating, of HVAC, of utility, lighting, and so forth, you'll find links to the various profile documents. And all of those are downloadable for free. You do not need to be logged in as a member, and just simply download them in PDF. Another question, so are they also available in binary format? They are. You can find them in the Landmark resource files binary. You'll find all of the actual files for those who are putting them into a network management system or those who are developing. And you'll find that we now have version 14.00 of those files available with fresh new documentation. And you can find those at www.landmark.org/LMRF, as in Landmark resource files. Now the question, are they available in XML? They are available in XML. You can transpose. They are transposed through a different website, which is types, types.landmark.org. And those files are transposed XML files. You can also generate the XML files yourself of your own device as well as of your standard resource files using the resource editor, which is available for free to all Landmark members in the member download area. It is also available to anybody who has purchased Echelon Corporation's Node Builder development tool. I don't see any more questions at this time. Again, I want to thank you all for joining. It's been a pleasure being able to share this information with you. And as I say, it will be available at www.landmark.org/webinars, where you'll find previous webinars, and you'll also find future webinars. So you'll be able to sign up for other information as well. Thanks again for joining us today. Much appreciated.
Thank you, Jeremy. Thank you, everyone. Have a good day.